Hello there, ATSEVS533 students. This is the third day of the third module of our course, and let's go ahead and keep moving forward and talking about the future of climate. Now, just to review, last time I told you about these four storylines, pathways, scenarios. There's different terminology for this notion. I like the term scenario best, and I think that's the most acceptable for this. But I also mentioned briefly that this kind of notation of A1, A2, B1, B2, it's kind of fallen a little bit out of fashion, if you will. These four scenario families that within them have sub-scenarios like A1B and A1FI and so on were created by the SRES, the Special Report on Emission Scenarios, which was an IPCC thing. And they were the ones who did the kind of work I talked about last time, where there was interdisciplinary work about making predictions about the economic and political and demographic changes, technology changes, and so on. And from that information, they got a hold of things like deciding how the amount of greenhouse gases in the atmosphere would change, or how the aerosol burden in the atmosphere would change, and so on. And this terminology of A1, A2, and B1 and B2 is still certainly very commonly used in the climate science community. And certainly, if you pick up a paper or you pick up a textbook about climate science and so on, they're almost certainly going to be using that terminology. But in terms of like modern cutting-edge research, there's a little bit of a problem as to how this was done. That wasn't really entirely thought out when they first created these SRES scenarios. These scenarios first thought out the socio-economic impacts and then figured out what the greenhouse gases emissions and other climate factors were going to be that were associated with those processes. In fact, if you just take some verbiage right out of the IPCC AR5, it says the SRES suite of scenarios was developed based on specific socio-economic storylines about future demographic and economic development, regionalization of the world's economies, energy production, energy use, changes in technology for energy development and production and distribution, agricultural practices, forestry practices, and so on. And that's all really important and so on. And then based on that, they came up with the inventories of greenhouse gases and aerosols and so on. In fact, you can actually get that information out of the IPCC report. There's giant tables of like, under scenario A1B, in the year 2032, this is what the greenhouse gas concentration in the Earth's atmosphere is. This is what the aerosol, the amount of black carbon in the Earth's atmosphere, and so on. And that's neat. And that's clever, but there's a small problem. We're trying to use that information as boundary conditions for a whole ensemble of models. Remember, that was the purpose of this. We're going to run these climate models, and this is going to serve as the boundary conditions. We're going to tell the model how much carbon is in the atmosphere. We're going to tell it how much mineral dust is in the atmosphere, and so on. It should have worked. It should have made them very easy to compare, because if I ran the Creighton climate model, there is no Creighton climate model, and somebody else ran the European Center for Medium Range Weather Forecast climate model, it should have been apples to apples, right? We both have exactly the same amount of carbon dioxide in the atmosphere, the same amount of mineral dust, and so on. But in practice, it didn't quite work, because, it's not terrible, but the philosophy has a little bit of a problem here. See, these models that we're talking about, these numerical models of climate, they have some representation of the carbon cycle in the Earth's atmosphere. They have ways in which the 7 primitive equations seven primitive equations don't change the amount of carbon dioxide in the Earth's atmosphere, but they have calculations where they talk about how much photosynthesis is going on, and so on. Each of the models has ways of describing how much carbon dioxide is being transferred from the atmosphere into the ocean, for example. And those are all going to be the same. They might not change hugely. The differences between one model and another might not be very big. And for that matter, each of the models has its own physics that explains what's going on. It's like how we remove aerosols from the atmosphere. There has to be calculations that involve how quickly those aerosols are removed by raindrops and so on. And I'm sure that all 35 models or whatever it was that the IPCC was considering all do it slightly differently, and I'm sure they all do it within a nice range, but that's all different. And that meant that over the course of a very long simulation, like a 100-year climate simulation, these differences sometimes added up to make the models hard to compare. It was hard to compare, let's just say, the Creighton model to, let's just say, the European model, because they didn't have exactly the same amount of carbon dioxide anymore, and they didn't have exactly the same amount of aerosols anymore. I mean, that was the point. We wanted to do that. We wanted to have the same exact amount. And so the folks behind the IPCC and related projects like AMIP, the the Atmospheric Model Intercomparison Project, and so on, they sat down and thought about what was really going on here. And they said, do we really care what's the amount of aerosol in the atmosphere? Do we really care, for that matter, even what the amount of carbon dioxide is in the atmosphere? What we care about is the impact of all that stuff on climate systems. And so what I really want to know is just what will the climate be if there's this much radiative forcing, or if there's this much radiative forcing due to anthropogenic processes. I don't really care whether it's the aerosols that are causing it, or methane, or chlorofluorocarbons. I want to know what the impact of a certain number of watts per square meter of radiative forcing is. We can then later reverse engineer what caused that radiative forcing. This was a pretty smart idea, and they basically said then, why are we bothering telling the model what the carbon dioxide concentration is? Why are we bothering telling the model how much aerosol there is in the atmosphere? Let's do this the other way around. Let's just tell the model, I want to know what the future climate will be if there is 1 watt per square meter of anthropogenic radiative forcing. I don't really care what caused it, because a watt is a watt is a watt. It doesn't really matter where it came from. Oh. And then I'm going to run the model again, maybe with 2 watts per square meter of anthropogenic radiative forcing, and see how the climate develops and so on. Oh. Well, now this is kind of smart. This is actually a pretty neat strategy called RCP. RCP stands for Representative Concentration Pathway, which I don't really love that name, but whatever, RCP. And RCP says that, well, since the forcing due to the aerosols is equivalent to the forcing due to aerosols, which is equivalent to the forcing due to albedo changes due to land use changes, who cares? Let's not worry about what caused the changes. Let's just say we're going to run some model simulations where there is 1 watt per square meter of radiative forcing. We'll run some model simulations where there is 2 watts per square meter. Later we can decide what we want. You know, what do we think is the true radiative forcing that anthropogenic processes are having on the atmosphere. This is really smart. We're not really going to worry right now how that happened. We're just going to say, we know climate is driven by these radiative forcings. In practice, there turned out to be 4 standard RCP pathways. They have names like RCP 2.6, RCP 4.5, RCP 6, and RCP 8.5. And that number at the end just tells us what the final radiative forcing that we are using in that scenario is. So, like, you know, RCP 6 means that we're imposing a 6 watt per square meter radiative forcing due to anthropogenic changes. Not really caring if that's more because of black carbon, or more because of tropospheric ozone, or more because of... I don't care. I literally don't care at this point. I just want to see what the model does with this information. For what it's worth, by the way, RCP 2.6 is too small. That is not a realistic amount of radiative forcing that's going to happen in future climates. RCP 4.5 is actually pretty close to what we called B1 in terms of its radiative forcing. B1, you might remember, is that sort of Star Trek future where we really use technology to make a more equitable, information-based world, information technology and services, and social justice, making population level off, etc. That's our best scenario when we think back to those SRES scenarios. The RCP 6 scenario pathway is very close to A1B, the so-called business as usual storyline, where we just keep finding fuel until eventually we hit peak oil and we just can't afford to keep pulling it out of the ground anymore. We had worse scenarios than that, like A1FI, the one that was so fossil fuel intensive, where we just use technology to keep finding harder and harder resources of fossil fuels to exploit. And that works out to be quite similar, actually, to the RCP 8.5 scenario. So their names are going to be telling us what they mean, and for what it's worth, they are actually a defined thing. Like, for example, here is the radiative forcing exerting on the climate in those 4 different scenarios. So, like, for example, you can see up until about the year 2000, the black curve there shows us what the observed radiative forcing on the atmosphere is, and you can see it wiggles around a little bit due to things like volcanoes and so on. But then we move forward with and see what the radiative forcing would be in each of these 4 different scenarios. And, you know, we're them leveling off at some known anthropogenic, you know, if we added enough carbon dioxide to the atmosphere to get to 8.5 watts per square meter of radiative forcing. Remember that at the present time, the total amount of radiative forcing on the Earth's atmosphere is, well, between the present and the pre-industrial period was something like 1.6 watts per square meter. So these are all big radiative forcings. This makes the models much more apples to apples to compare. If I take the Creighton model and I just tell the model, I don't care about how much carbon dioxide, that doesn't change anything. I just want to know if I impose a 4.5 watt per square meter radiative forcing, what does the climate do? And then if somebody running the European model takes it and gives it a 4.5 watt per square meter radiative forcing just like that, this is apples to apples. We are comparing equivalent runs of the model. This is a better ensemble strategy, which is why this has become kind of the fashionable way for climate science to be done. It doesn't bog itself down in, oh, there's more social justice in the 2.6 scenario or something. I mean, that's a hard thing from the point of view, from the cold point of view of what's going to happen to science, to the climate system. This kind of makes more sense. All right, so that doesn't mean though we can't reverse engineer from these scenarios. These RCP pathways, what would the amount of carbon dioxide need to be to cause that? Or what would be the amount of methane, or the amount of halocarbons, or nitrous oxide, or whatever. And so, because certain chemical processes in the model usually do need to know things like how much halocarbon is in the atmosphere, the pathways that we've defined, they are actually, you know, there is a defined amount of carbon dioxide at each year. There's a defined amount of methane each year. And you can see they get pretty out of control. I mean, like RCP 8.5, our worst scenario that we're talking about here, carbon dioxide concentration gets really close to 2,000 parts per million by the year 2300. Keep in mind, it's right around 400 right now. So I mean, that's an enormous amount of carbon dioxide in the Earth's atmosphere. And you can see there's a variety of different ranges here. You can see, for example, the RCP6 peaks around 800 parts per million and so on. Obviously, I don't expect you to memorize any of this, but I just wanted to show you, you can back out of this information. You can recover what the amount of methane, halocarbons, carbon dioxide would need to be in a realistic distribution of energy sources and so on to create those anthropogenic radiative forcings that are what is the basis of those RCP pathways. Wow, that's a complicated way to think about it, but when you start spending some time on this, that makes really good sense. That's actually a really smart way to be picking apart how we're going to compare a whole ensemble of model runs. And so that's why this has become much more, it's more what the smart money kids are doing in climate science, okay? But that doesn't change the fact that there's, you know, decades of research using the other notation and so on, and so we're going to kind of tie them together. Let's answer a couple quick questions before we move on to part 2 of this lecture here. Which set of the storylines, or pathways, or scenarios, whatever terminology you want to use, was crafted by the Special Report on Emission Scenarios, or SRES? Was that the ones that would have names like A1, A2, B1, or B2? Or was that the ones that have names like Representative Concentration Pathway? Which of those are the ones that the SRES created? Let me know, make a choice from those 2 options, and get a little feedback before you move on to question 2.